Hello. This module will show how satellite images can provide valuable information to improve public policies in cities. The decision makers and the ones in charge of urban planning have to tackle numerous issues in their cities. However, they often lack updated data or they don't have the data at all. This is the case for vegetation maps in urban areas. There are few advantages in using satellite images to map urban vegetations, and we will see some of them. Satellite images are now available for free or for a fair price from various providers. Another advantage is that the images provide continuous information across space and time, and therefore enable the users to look beyond the borders between public and private space. The methodology to extract information on green areas from satellite images is fairly straightforward. We can read about the main issues and concerns in urban areas in the European Urban Agenda. These issues actually apply to most of the main cities in Europe. To measure and to understand the positive effects of the green component of the cities, we can highlight some specific points. Vegetation absorbs part of the rainfall and limits the strength of the rainfall impact on the soil during severe weather periods, which contributes to the minimization of landslides. Biodiversity conservation policies are not only an issue in rural areas, cities are also an interesting environment with a lot of biodiversity. To be efficient, these policies need to rely on urban green networks. On another hand, numerous studies have shown the benefits of urban vegetations for the inhabitants. It's a good asset for well-being in cities with a positive impact on health. A city can be influenced by the urban heat island effect, for example. This point is critical in the context of global change, and cities can be very sensitive to this phenomenon. Among various solutions to this problem, urban vegetation is a great asset to cool down the urban areas. The urban vegetation is usually not well known in the current database, especially when we look at private areas. It's an important lack of data for the public policymakers who need inventory of the situation of their metropolis. They need also data to assess the efficiency of the strategies that they are actually implementing. So how can satellite data contribute to the knowledge of the green areas? Let's now say a few words about this and see how remote sensing methods can be used to map the vegetation. First of all, we need to understand what a spectral signature is. Most of the optical Earth observation satellites have sensors which are able to measure energy in different wavelengths, specifically in wavelengths corresponding to green, red, blue, and near-infrared. Each surface on the ground absorbs a part of the energy and reflects another part, depending on the kind of ground surface. In the case of the vegetation, as we can see here on the left figure, the vegetation has a high absorption in the red and a low absorption in the infrared. We can also observe this in more detail on the figure here on the right, which is showing the spectral signature of some ground surface types. In the human visible part of the electromagnetic spectrum, here on the left, it is not easy to make the difference between bare soil and vegetation. But in the infrared, the difference is actually quite obvious. We will now take advantage of the specific spectral signature thanks to a simple indicator called NDVI, which means Normalized Difference Vegetation Index. This index allows us to map the vegetation in a simple way. You can see here the formula on the slide. There are also other indexes that can be used, but NDVI is definitely the most common one. Of course, channels red and infrared are needed, but the resolution is also a very crucial issue. Very high resolution images are the best solution to map the vegetation, especially at the cadastral parcel level. Pléiades, 50 centimeters, fit to this need for urban areas. Also, Sentinel-2 have a lower resolution, 10 meters. This lower resolution can fit for rural green areas and monitoring land consumption. Sentinel-2 are easy to get. And it's possible to choose easily the best season. The season for the selected images has to be adapted depending on the local climate. So for example, in France, it should be good to select an image between March and September. These data are available thanks to Copernicus. We will see here which Copernicus dataset can be useful for green areas. Firstly, there are the Copernicus contributing missions providing satellite images. The optical missions with near-infrared and red bands as Pleiad with very high resolution for urban areas, or Rapid Eye, SPOT, with high resolution can be found in the data warehouse of Copernicus. This is, however, only accessible under certain conditions. The free, full and open Sentinel-2 mission and its full constellation will provide images with NIR band 8 and red band 4 about every day at 20 or 10 to 20 spatial resolution. Another interesting service is the Copernicus Land Monitoring Service. The Copernicus Global Land Service provides access to pan-European high-resolution layers of forests and grassland maps for 20-meter resolution satellite imagery, and they are actually updated every 3 years. The demonstration will show how to take advantage from the very high-resolution optical satellite data to have a global view of green areas in an urban context. The methodology that we propose here doesn't need specific skills in remote sensing or GIS. It is a step-by-step process, and you should find it actually quite accessible even if you are a beginner. We choose the Pleiad data as very high-resolution satellite data for this demonstration. The software we use is QuantumGIS or QGIS. Similar steps can be done with Sentinel-2 data and SNAP software. We will use the free toolbox provided by ESA, the Sentinel Application Platform, or SNAP. First of all, you open the satellite data using the menu layer, and then you add the raster layer. Here, the image is in TIF format, which QGIS, thanks to the GDAL driver, can open in a wide set of formats. In order to see the landscape in right color, some parameters have to be adapted. For this, you have to right-click on the image layer and left-hand side menu, then go to Properties. The Style tab in the window opens. The step will enhance the dynamic of the image. The tool will stretch the histogram here by loading only the values between 2% and 98%, and you can actually adjust it to your own setting. Then you click on Load, and you finally apply. So here you can zoom in the area of interest. Now we will process the NDVI computation. QGIS provides a very useful raster calculator that you can find in the raster menu. The windows of the raster calculator is now open, and in the frame raster band, you can see the 4 different bands. Here we assume that the user has checked the order of the bands. This knowledge is actually quite fundamental for the next steps that we will see. In this case, we have band 1 as red, band 2 as green, band 3 as blue, and band 4 as near-infrared. For instance, for Sentinel-2, it will be band 2 as blue, band 3 as green, band 4 as red, and 8 as near-infrared. Now you have to write the formula in the raster calculator expression frame. Type the formula using raster bands and mathematical symbols and use the NDVI formula. Don't forget to name your output layer. The NDVI values are black, with low values for water, in general negative values of NDVI, and white, with high values close to 1 for vegetation. To see it clearly, we will use a new style for the NDVI layer. Right-click on the NDVI layer, go to Properties, and then to Style. Select as in the red boxes. Below value, you can fix the thresholds that will enable to separate the different land uses. The threshold can be different depending on the kind of images, so you have to adjust it properly. The threshold chosen here usually works well with Pleiad images. If you just want to see the green areas, you're done. If you want to get a layer with green areas, you have to create a mask as following. Go to the raster menu, and then click on the raster calculator. Then create the mask using the formula NDVI bigger than 0.3. Here is the mask. Raster with value 1 for green areas and 0 for other pixels. You can use some filters in raster menu as post-processing. If you want a vector layer, you have to polygonize using raster menu, then conversion, and then polygonize. The mask here is now vectorized, with polygons values at 0 and polygons vegetation values at 1. We need to extract the vegetation polygons. So use the selection tool, epsilon, in the toolbar. It opens the attribute table and asks for a formula to make the selection. Select polygons where dn equals 1. Then you save the selected polygons using right-click on the vector layer, then Save As. And in the dialog box, do not forget to check Save Only Selected Features. Then you get the green area vector layer. You can also use some filters to improve the results. For example, you can decide to remove very little areas. You can add any information on areas using the attribute table tools. Using the field calculator, you can add a field area as described above. On this new field, it is possible to make some basic statistics using vector menu and then basic statistics. It gives information on the total area, the minimum, etc. Doing this with time series of pictures allows you to see significant changes. As conclusion of this module, this method gives a global view of vegetation, providing that the thresholds to identify vegetation are adapted to different areas. Other more complex methods are used to derive vegetation maps, but this one can give a first idea of green areas. Doing this method step by step can be actually quite time-consuming, so this is why Serema developed a plugin to assist the user in choosing the threshold and creating these green area maps. We should like to thank Serema for providing us with this use case, and thank you for watching.